I don't know how many people know what is IPD work, what it stands for. So it is individual participant data meta-analysis in working populations. Because usually when you do meta-analysis, you just search literature and then pool the results together. But the idea in this consortium is that we collected the individual data and only after that started to pool. And now I try to explain why we came to that solution. So these are the questions I am talking today. So first I describe a bit the landscape when we started this IPD work. What were the main problems we saw in the evidence, and then how we thought these problems can be overcome, and then we established this IPD work consortium, and then I tell what kind of results that consortium has produced. And then lastly, I explain a bit how these have, what are the actual practical implications of these studies. Has it changed anything, or is it just saying the obvious? So I think there are three problems in the evidence, and I try to explain why. So one is, first let's show who we are. So IPD work consortium is I think 61 researchers from European countries and now also from the US, and it's only possible because of this collaboration. So that's the great thing here, that this is really a collective effort to achieve a bit more with our data sets. So that was one of the problems when we started. If we look job strain, which is probably the most commonly used indicator of work stress, it means that you have a lot of work to do, a big workload, but little control over your work. So that's the stressful equation in a way. And there has been research on this stress in relation to different disease outcomes, and especially in relation to cardiovascular diseases, because it was thought that that's the system which is badly affected. But the problem is that if you look at these findings, so these are relative risks. So if it's more than one, the relative risk, it means that the study suggests that if you have job strain, you have increased risk of coronary heart disease. If it's less than one, it says that actually those people who have job strain might have lower risk of coronary heart disease. And now when we look at these figures, we see that some of these studies find no relation. So you can look, these are confidence intervals. So when you have below and above 1, it means that it's not statistically significant, because at the same time the data says that it can be lower and higher. So you have no risk in some studies. Some studies suggest that if you have job strain, your risk is doubled. Some studies says that it's only 50% its increase. Some says that there is again no increase, and there might be even some protective effect in some cases, and some report very, very high associations, 9-fold risk of coronary heart disease if you have job strain, and so on. So which one we believe? So there we are. So if this is true, then we know what to do. We really put all our effort to prevent all kind of job strain. If this is true, then we shouldn't put our money on these kind of things, at least in relation to coronary heart disease. So I have here tried to compare these estimates to those which we know for known risk and protective factors for coronary heart disease. So here you see, in some of these studies we saw that the relative risk was 0.9, suggesting that there is some kind of protective effect, and the highest risk was 9-fold in one study, which is extreme risk. And here you see that these kind of 0.9, 0.8, they are actually protective effects which relate to, if you use statins, you decrease your risk some 20-30%. If you have a very healthy diet, you again decrease your risk of coronary heart 10-20%. So it's having on top of that top strain something that it reduces further? Or is it going so that actually it's doubling so that it's equally bad as being morbidly obese, or equally bad as if you are a regular smoker or have high blood pressure? So here we are. We have all this evidence. We don't know what to believe of those. And if we don't have any clear idea which one we choose to represent the best evidence, then how can we do any policy implications? So one way is then that, all right, let's look literature and see what researchers in this area are citing, because if that in a way reflects that the best studies are cited most. And we did that. So we took all studies on soft strain and coronary heart disease which were published more than 10 years ago, which means that there was at least 10 years time for researchers to cite these studies. And I'm here in a way because the people who wrote this article, they study this one and that one, so it's the worst and the best. So we are in a way impartial here. But here are citations for these studies. It's a bit old, but anyway, you can see that it really varies. This study have been cited more than 350 times, and this is less than 80 times. And now, if we do an interesting comparison, which kind of relative risks are cited most? Oops. The higher the risk, then the more you get citations. Okay. Is that then true? So is that the true value then, because it's cited most? I said that there must be a citation bias. It's so much easier to write top strain is related to is associated doubling of your risk. It's much easier to say than there might be some weak association. And then there was a person in audience. No, it's because these are methodologically more superior, and that's the reason why they are cited most. All right, there was a review article which reviewed all these studies. We were not part of that review at all, and none of these people who were in these studies. Let's see whether that person in the audience told the truth. So one thing here is that what affects citations is definitely the journal where you publish your studies. So this was in BMJ, and so that gives you some citations. But this is the scientific quality of the study. Independently reviewed. So people in these studies were not part of these reviews. So we can't believe these researchers what they cite. So that's now seems to be clear. So then the other thing was that, and if you look what we see here, so let's say that these studies are, if these are the best in terms of methodology and numbers, we can say that we don't know based on these studies whether there is an association, whether it's increasing or not. But these studies cannot rule out a 30-40% increase in risk. But they also can't rule out some protective effect. So there we are with the evidence. So that's problem number one. Then we calculated this because we were so amused that the higher relative risk, the more citations. So we calculated that every additional 10% increase in your relative risk increases your citations 16 times. Okay. Oh, so I think it's not only researchers who are exaggerating these kind of things. This also happens in the media. So we had a paper which looked, if you work very long hours, whether you have increased risk of having heart attack. And the first day it came out, this was the figure in for example, Telegraph. It looked very like that. This is probably how it looks like next day. No, this is still the same day. Next day. Then later in the evening. All right, and then the last day. So media has own agenda too. So first this was on news, but then you need to be more extreme to get your news out. Sorry.
To change the slide.
All right. Okay. Yeah. Problem number 2, what we also found problematic, is that there are no standard measurement for job strain. There is no gold standard you should measure like this. Instead, there are a huge number of different measures. So we looked all these studies we had in this IPD work, 17 studies at that time, and we found that there were actually 11 different sets of questions to measure job strain. Then we know that there are articles which recommend that you can actually combine these questions in a different way to get the job strain indicator. So you have a quotient system, quadrant term system, quadrant term using national means, and linear term formulation. So you have different, even if you have similar items, you can create the job strain measure in at least 4 different ways. And they are not totally overlapping people. So there are at least 44 different measures for job strain. And if you now think, you start to think, do people publish? Could it be that it affects slightly that they use the best indicator, so that which works best, and publish those results? So that came as a one pressing question for us. There has been, so this model has been studied, I think, 30, 40 years. And the problem is that there has been very different findings. So one debate has been that which one is more important? Is it job control, which is the important one, or is it job demands? The theory says that you need to have both. But there have been, these 2 reviews were published, I think, within 1 year from each other, and they had opposite conclusion. Then there has been some people, some researchers says that, all right, it's more like it's more harmful for men. Other people says no, it's more harmful for women, and some people think that it's bad, especially if you are young, because then you are exposed for a long time. And other people say no, it's bad if you are old, because you already have high coronary heart disease risk, in a baseline risk, and then if you have this on top of that, then you get the disease. And then are people who says that no, it's spurious, the whole association. It's all about socioeconomic stratification, which is doing this. And then there have been recommendations that you should do these kind of subgroup analysis in a way to look which one of these is most important. We saw that the problem sometimes in these subgroup analysis is that you run to quite small sample sizes, and then you can have fairly random results. this kind of subgroup analysis was, I think it was very much emphasized in some of the alcohol journals, and we actually then wanted to demonstrate that you can also, if you don't know what you're doing, you can get fairly strange results with this subgroup analysis. So we just look the association with hazard ratio of alcohol use in relation to CHD, and I think this was hazard ratio for experiment during the follow-up. If you don't drink at all alcohol, and then we took the zodiac sign, and we divided the study population, and all right. So if you are Capricorn or Cancer, you need to drink alcohol, but all the others, no problem. And this is simply demonstrating that if you have small sample size, you get these random findings. You need to know when you do this kind of subgroup analysis that what you are doing and that you have enough cases. And then comes the final problem, which is publication bias. I want to demonstrate that so that if we imagine that we all are editors of journals, so we have space for one new article in our next issue. We got 4 papers, all looking job strain and coronary heart disease. All are methodologically equally strong, so they are exactly similar. So you have study A, which shows that there is 1.5-fold risk, and if you look these confidence intervals, this is statistically significant. Then we have a study B, where the effect estimate is slightly lower, but if you look confidence interval, you see that you actually cannot say for sure that there is an increased risk because this is not statistically significant. You have study C, which is saying that actually it's related to quite large risk, 1.9-fold risk, almost doubling the risk. But again, it's not quite statistically significant, so there is some kind of uncertainty. And then we have this last study, which actually suggests that there is absolutely no association at all. I think many editors would think that, all right, we can't conclude anything based on this. This suggests that there could be quite bad consequences of job strain, but you can't be sure because this can also be a random finding. And the same here. But here you can draw a conclusion. It increases your risk. So probably let's publish this study. And that's the way publication bias operates at the level of editor. The other thing is that if we do research and we look for different things and we get these kind of results, it's very likely that we write up this study, and these others might wait. So there are many ways how this publication bias can operate. And the problem in cohort studies is that typically cohort studies are not registers. So we don't register in advance what we will do. This happens for trials. So if we think trials, which is a stronger study design, so we have population, there is randomization, and you have group, exposed group and non-exposed group, and you are blinded so that you actually don't know which one is what when you analyze the data. And you have defined these exposure and exposure and non-exposure before you start your analysis. So these trials are registered, and then you look what happens. The problem here with cohort studies is that we don't have this randomization, so this is something we have to deal with, so that we try to adjust for confounders and these kind of things. But here is something which is more problematic. There's very little protection against all kind of post hoc decisions. So, for example, that all right, we analyze slightly, and all right, this looks like that. We take that measure rather than that measure. So there is this kind of flexibility which can bias our total evidence. And the other thing is that multiple testing is rarely accounted for. So if you really do 40 different indicators for your job strain and you publish only using one, so then you don't take into account the multiple testing problem at all. So this makes the observational evidence more fragile. The publication bias is nicely actually demonstrated in studies which looked medical trials on antidepressants, how effective antidepressants are. So because these trials are all registered, you know what the trials were and which one published and which one did not. And this is what you see. When you have a positive finding, that part was published. And with negative findings, only that small part was published. And then unpublished data, you see that most of them were null findings, so people didn't write them up. And obviously, the full truth comes when you combine these two, but basically you see only this if you read publications. Okay, now I have tried to demonstrate that these are the problems, and we tried to address these problems, somehow make it better than earlier, previously. So what we did, so we collected the data from all these studies in two stages. We first collected data on exposure variables, and we did not take any data on outcomes. And we harmonized the job strain and effort reward and these kind of definitions, and then we published those. So then there's no way of changing it anymore, so that's fixed. And this is like this is a bit similar like in clinical trials, the trial registration. And so that was something we tried to mimic a trial design in this respect. The other thing which we wanted to address was the publication bias, because the problem is that if you have, as we looked these 4 studies, where you have estimates and you can't say that is it increased risk or not. So that makes it difficult to publish. But if you have very, very large sample sets, then even the null finding can be published, because you can say convincingly that there is nothing. And this is to demonstrate the power of having large samples. So now we are looking systolic blood pressure in relation to cardiovascular death using prospective study collaboration data. So here is the level of systolic blood pressure, and this is the relative risk of death. And these are age groups. And with 5,000 people, you sort of see that there seems to be some kind of upward trend, but you really don't know. It looks fairly muddy. When you have 10 times more people there, now you start to see that, okay, there seems to be upward trend in all these different age groups. But again, the confidence intervals are quite wide, but that's what seems to be there. And only when you have 10 times more, now we have 500,000 people, you see it. There's an association. There's no doubt about that. And the same is true if there's no association. So here it will look like that, and then it's mess here, but here it would show that it's totally flat. And that you can publish. It's easy to publish because you give strong evidence that there is nothing. So that's the reason we thought that we also want to have a very large data set to be able to publish also null findings. The other thing which we wanted is that we wanted studies which have had already previously published their findings on job strain and CHD, and other studies which were not, just to see whether there is this kind of publication bias operating. Let's look at the results. So these were the initial studies here. So COPSOC is your study. TVEX is your study. I think IPAV is your study. Is that all? Yeah. Altogether 200,000 people, followed up some 10 years when how many people got 2,300 got coronary heart disease, and these were all these people had no known coronary heart disease at baseline. Okay. Now we then look how the first thing was obviously to harmonize the questionnaires. So these are the different studies here. These are the questions which were in most of those, and this shows that in each study which question was available. We then used those studies which had all these questions to look that if you have only 3, for example, do you get roughly similar categorization for job strain compared to if you have all 5 items, and the same here. And that's the way we built the job strain variable, so that although there were a different number of items, we could show that actually they are picking up the same population, more or less. And that was published first. Then we started to look associations with different diseases. Coronary heart disease. It's not increasing your risk 9-fold, and it's not protective. We can see that it's according to these studies, it's something like 1.2-fold, about 20-30% it increases your risk of coronary heart disease. And the confidence interval is from 10% to 37. And then we try to test whether this association is biased. For example, if we measure job strain for a person who next year got CHD, probably the atherosclerosis was fairly advanced or already when we measured the job strain. So there is possible reverse causation. When you have atherosclerosis, you are more tired, you might feel things more stressful. So we took out first 3 years of follow-up and started the follow-up after 3 years. And then we did the same, we took out first 5 years, and this is to reduce reverse causation. And we see that it didn't affect the estimates. They are there still, which means that reverse causation cannot explain this finding. Then we adjusted our analysis for different covariates, socioeconomic status, all kind of health behaviors, the Framingham score, which is a composite score of standard coronary heart disease risk factors, CHD, cholesterol, hypertension, smoking, diabetes. And we see the association all the way here. It doesn't change between countries. Here we see some evidence of publication bias. In 3 studies, the job strain coronary heart disease association had been published previously, and pooling those datasets, we got 1.4-fold increased risk. Those which had not published the association previously had only 1.2-fold increased risk. Both had an association, so that's reassuring. So we were fairly confident that this is the true, roughly the increased risk what is related to job strain. Then we thought that, okay, now we have this big data, and then we have all the previous studies. If we pool all available data, what shall the association be? So this is a meta-analysis where we always add the next study and then analyze it again. So we start from the early studies here, and you see the confidence intervals are very wide. The next we add to this Reed study the Johnson study, then the estimate changes here, increased risk, again still very wide, and so on, so on. And you see that somewhere here, Cooper, by the way, this is Whitehall study, shows 1.37, and then there have been huge number of new studies, and it has not changed anywhere. So it is roughly 1.3. Then after IPD work, there was a further study published in Scandinavian Journal, and it's again 1.3. So there are quite huge evidence that that's roughly what the finding is, which suggests that if you now start to think that let's send to funders a funding application that I want to study job strain and coronary heart disease, you need to have 2 million people to change this anyway. So. I never learn. Then we looked these subgroups, because there had been this discussion that it's men and not women, it's young, not older, and it's all confounded by SES. But we actually did not find any real difference here between subgroups. So you see men and women. You should perhaps more look these confidence intervals than the effect estimates. So you see that these are really overlapping. The confidence intervals are really overlapping. And you see the same thing in younger and older people and in all socioeconomic groups. So in that sense, it looks like very general, very universal association. Okay, so we looked similar kind of things in relation to long working hours. I'll go to these a bit later. But very recently we have also looked other commonly used job stressors, whether if you have not only job strain but also effort-reward imbalance. Effort-reward imbalance is another measure of stress. So you put all your effort in the work and you feel that you don't get any reward at all. So that's effort-reward imbalance. So we try to understand whether there is a synergistic association, so that if you have this plus this, it's more than the sum of these two. Or is it just additive, so that it is actually, if you have these two, it's like summing up the effects? Or is it so that if you have either of these two, it doesn't matter anymore if you have also the other, because you have anyway increased risk of coronary heart disease. And this is what we see. So comparison group which did not have effort-reward imbalance or job strain. Then the next group which had one, so they have either job strain or effort-reward imbalance, but not both. And you can see that it's roughly the 1.2 again here. And those people who had both, unlucky people, then it's 1.4-fold. So there is some kind of dose response clearly operating there. It's not synergistic, but it's looked like additive. Stroke. So vascular system it's not only heart. Basically, if you damage your vascular system, it is also possible that the infarction is in your brain rather than in your heart. So let's see what it happens with stroke and job strain. So this is what we see in IPD work. We see that if you have all strokes, if we are looking all strokes, there is hardly any effect here it's not at least statistically significant. If you look only ischemic stroke, which is when you really have atherosclerosis, and that's the background for this disease, there you see an association, which is very similar as we see for coronary heart disease, which is actually what we would expect. But if you have hemorrhagic stroke, which is a different etiology, then top strain is not related to that. Okay, so then we went on because we know from Japanese studies that they have this overworking, working very long hours, and they have in the insurance system even that if you get stroke and you have worked long hours, they are compensated. It's like a occupational cause of the disease. We have looked also working very long hours. There were very few published studies if you want this kind of prospective design. Only one which showed that if you work more than 10 hours per day on average, it's 1.4-fold increased risk. We added our cohort studies here to X, COPSOC. Now we have 2 COPSOCs from your institute. And you can see that really it gives a very consistent finding that it's roughly 30% increase in the risk of stroke. Yeah, so my obviously then solution was that all right, if it's actually it was if you work 11 hours or more, then you have this risk. So we decided in our group that we work 10 hours 59 minutes, and so we don't have any risk on average. But actually it doesn't go like that, because if you now look, there is actually a dose response, so it's not possible to do like that. So it increases gradually, and actually this is in that sense good, that it gives you more credibility that there is some kind of real behind this. And now we look different ways of testing whether this association is true or confounded or biased. So we are looking, we exclude from the beginning of the follow-up 3 years. We do minimum adjustments, we do maximum adjustments for all kind of stroke risk factors. We look whether the ascertainment method, how you ascertain your outcome, affects the finding. What about published and unpublished findings or region? And look how consistent it is. So it's always 1.3 or 1.4. Very, very little variation, suggesting that this is again something which is likely to be true. This is when we look then men and women separately, and old and younger, and again we don't see any differences between these groups. All right, clinically meaning. Is this clinically meaningful? Now, in working populations, stroke is very rare. So in our case, we had 10-year follow-up. Approximately 6 people had stroke per 1,000 workers during these 10 years, if they worked very long hours. And if you work standard hours, it's 4.5 people get a stroke. So the difference is 1.5 events per 1,000 people per 10 year. Population attributable risk is 6%, which actually is not very small. So basically, this is rare, but the population attributable risk. This means that if you are able to remove, if we believe that this association is totally causal and we can remove all long working hours, then we would see 6% less stroke cases. So this is not trivial actually. So because we know that cardiovascular diseases are multi-etiological, So this makes a contribution. Let's look at other diseases. Diabetes is important because it's increasing quite a lot. Here we see a bit similar kind of situation. So if we looked now different groups based on other lifestyle habits, so whether you are physically active or not, whether you smoke, whether you drink, whether you are overweight or not. So you can see that actually in all these cases, so if you are obese and on top of that you have job strain, you see that it's slightly higher risk here. So it increases always a bit. The same here, if you are physically inactive and on top of that have stress, your risk again is higher. You are more likely to develop diabetes. Physical inactivity the same, and heavy drinking. This also shows that obesity is the main risk factor for diabetes. But you can see that there is a slight effect in all cases if you have job strain in relation to diabetes. If we look at different subgroups, now actually is the first time we really see that actually these subgroups might matter, because and so now we are not looking anymore job strain. Now we are looking again the long working hours. We don't see very clear associations at all with long working hours and diabetes, except low SES people. There we see. So you see that there is a gradient. And this could be that there is something real there. I mean, jobs are very different, and if there is this kind of sedentariness and these kind of things behind that, then it can make a difference if you are working in a low SES job. This is another situation where we see that running this subgroup analysis is actually useful. Now we are looking at job insecurity and increased risk and risk of diabetes. There is again a slight increase in those who are in insecure jobs. And now when we looked these subgroup differences, we see that we don't see any difference here in terms of age group or sex or actually SES. But you can see that in studies where your diagnosis of diabetes is electronic medical records or measured examination, clinical examination, there you see the association. If it's self-report, which is less reliable, you don't see it. The same if you rate the quality of the study in terms of all kind of quality criteria. Again, high quality studies show the association, low quality don't. Then we see that in the United States we don't see any association, but the problem is that all the data there was based on self-reported outcomes. So actually this doesn't reflect regional differences, it reflects differences in diagnosis method. But this is useful in a way that actually it gives an idea that yes, there is something. Cancer. This is quick. There is absolutely nothing. It's flat. And that's the beauty of having a large study. We can really say that it's, if there is anything, then it must be quite little. Now we go to the last thing, which was what are the implications. And this year there was new European guidelines for cardiovascular disease prevention in clinical practice. And there, these IPD studies were those studies which were referred to when recommendations were made for psychosocial factors at work and prevention of cardiovascular diseases. So the system in European guidelines goes so that they rate the level of evidence. So the strongest evidence obviously comes from clinical trials or meta-analysis of randomized clinical trials. And the second level comes from very large non-randomized studies like IPD work, or if there is a very small number of clinical trials. And then the lowest quality of evidence is if that's some kind of consensus opinion or small studies or registered studies only. Then the other thing which is behind these guidelines, they also have rating how strong the recommendation is. So we have a strong recommendation which is recommended when the evidence is sufficient to really say that there is benefit of targeting that risk factor and treating it. Then we have less strong recommendation which should be considered or may be considered, and that's class 2, and so typically all kind of observational studies could only have this kind of recommendation. And then we have again quite a strong recommendation which is this class 3, which is that it's not recommended. If it's very clear that there is not an association, we can say that no, it's not recommended. So this is the system, and one of the main principles which is good to understand here is that with cardiovascular diseases, there are always many different causes. And in terms of prevention, it might be better to look many causes rather than just one. And this is the example they give. So let's think. We know that if your total cholesterol is more than 5, it's high, and it's normal if it's 5 or less. Okay. We have a female person, age 60, with cholesterol 7. Systolic blood pressure 120 and not smoker. Then we have another person who is a man, same age, normal cholesterol. So this woman had high cholesterol. This man has normal cholesterol, but slightly increased risk of coronary increased blood pressure and smoking. So here we see which one we give statins. It's probably not this one, because the absolute risk is 2% within the next 10 years to have a CHD event. Whereas for that person who actually have normal cholesterol, the risk of having cardiovascular disease is 10 times bigger. So if we only looked cholesterol, we would rate wrongly these two people, badly wrongly. So all these risk factors need to be taken into account when you do a recommendation. We'll come back to that because that clearly plays a role here also. So what is said about chronic stress at work? In the guideline, they say that chronic stress at work, long working hours, psychological demands, unfairness, job strain, predict arterial disease, coronary arterial disease in men. Hang on. In the finding, it was men and women, and it was the same in both cases. Why they say only men? And then they said also stressful conditions outside work is also bad. So I was thinking, what's going on? Why they are reading so wrongly the evidence? Because this evidence is our IPD study, which shows that there is absolutely no difference between men and women. Okay, this is not the only thing. Yeah. Then the rationale for targeting psychosocial factors is that it could contribute to developing coronary heart disease or worsen the prognosis, and they also might be a barrier to lifestyle changes or adherence, treatment adherence, so that you, if you are stressed, you don't take your medication. And then they said that this is the way to assess psychosocial risk factors. So one is, do you lack control over how to meet the demands at work? So this is clearly a job strain question. And then the other one is your reward inappropriate for your efforts? So this is effort-reward imbalance. So these questions, all right, this is consistent with evidence. Recommendation, so it was class 2 and the higher class 2, so it means that should be considered. Level of evidence is B because it was not trial, it was non-randomized study. Psychosocial risk factor assessment should be considered to identify possible barriers to adherence. And now, in individuals at high risk or with established CVD, it wasn't in the finding that it's only those people. Okay, we go back. Why it goes that it's only men and why it's only those who have high CVD risk or already have a disease. I think we need to go here. So the reason is that we have the relative risk, which is about 1.4-fold. And if we think to add to that risk, for example, for that female employee here, who has something like 2% increased risk of cardiovascular disease. So it would mean that that risk increases to 2.8. So it's less than 3% still. But that man, if that has on top of that risk profile top stress, this increases to almost 30%. Then it makes a difference. To see. So basically that's the reason why in the guidelines they said that if it's seen in men and you should target it if a person has a high cardiovascular disease risk. A high cardiovascular disease risk is for people who have 20% likelihood of having attack during the next 10 years. So that's the thinking behind those guidelines. So now I start to put things together. So benefits of big data having this kind of consortium. Clear benefit is that you have improved precision. We have these confidence intervals which were quite narrow, which is good. So this is something which we can then rule out chance finding. So what we see is probably it's not attributable to chance. And this helps especially in relation to subgroup analysis, which typically are underpowered, but in this case they are not so much. A third benefit of big data is that you can convincingly show that there is no association. So this is a big advance. And in that sense, you can say that there is reduction of research waste. I mean, these all kind of once you have this kind of result, other times a different result. So it's more like last word research. Actually, there was in Finland our funder, which was the Finnish Work Environment Foundation, when they got this job strain CHD finding, seeing that all right, you need 2 million to change it, they just announced, don't send us a research application on job strain and coronary heart disease anymore. We don't fund it. So in that sense, it could reduce waste. We didn't know that, oh right, that's our area, but okay. And visibility is the other thing. So the good thing is that usually when you have big data, it attracts media. So in our case, for example, especially this long working hours and stroke risk, that was everywhere when it was published. And And there is this kind of altmetric statistic. I don't know whether you have heard altmetric. So it's something, it's an automatic system which calculates how much different research findings are in social media, in tweets, in Facebooks, in media articles. And this long working hour study was 2015, the 12th in the world. So the study which was most in media was antibiotic, and then there was this autism MMR vaccination, which was a lot of there, and this kind of thing. But a work-related study there, that's nice. And finally, there are also some drawbacks which are good to remember. One is that this harmonization is very time consuming, and it takes, you can't usually do it totally perfectly. In our case, for example, we didn't get anything out from the first 2 years. It was only harmonization the first 2 years, and our funders were a bit nervous that, hang on, you should get something out, but it was worth, because then it has been much easier. Then the other thing is that with big data, you can only look very simple associations. You can't build some complicated models where there are many different things. You are looking more like very much like main effects only. So it's more like hypothesis testing rather than hypothesis generating. So I already told that it might shift funding streams, and then it's very important to remember that all the biases which can happen in small studies, they also can happen in these big studies. And the problem is that if you really put forward biased or confounded findings, I think the damage is much more than with a small study. So that's the other thing. I think that's more or less what I wanted to tell you. Okay, thank you.